everyone, welcome to this episode of Kutu. Today we're going to be exploring a lot about systems of inequalities and applications of it. Before we begin today, you do need a few materials. Make sure you have a copy of today's notes. You do need a pencil, a ruler, and some different colored pencils. I do recommend having 2 or 3 different colors available so that you can clearly see your solution region when graphing. So we've done a lot of work with systems. We know that systems of equations, when we solve them just mathematically, we're looking for the point of intersection. But when we're looking at solutions to systems of linear inequalities, we're really looking at a range of values, right? We have infinitely many solutions, but we really want to analyze what that means in the context today. So today, your goal is to be able to apply what you know about systems of inequalities to solve, graph, and analyze the solution to real-world problems. So let's get started. When we look at each problem today, please make sure that you're looking and thinking about the following expectations. The first thing you should feel comfortable doing is defining the variables. Every problem today has a few unknown values. Your job is to determine, okay, what information in here is unknown and how am I going to use that for my let statements? Once you've defined the variables, you're going to use all the little clues in the problem to identify the system. In each word problem today, you're going to see certain constraints, and that's going to lead us into each of the inequalities in our system. After you've created the system, you're going to graph the inequalities using boundary lines, understanding the difference between a solid boundary line versus a dashed, and then looking at test points in order to determine the direction in which we should be shading. Finally, we're going to analyze what points in the solution region means. You should write a solution sentence, and it says here include 2 possible solutions, but it really depends on the context, and we'll talk a little bit about that as we move forward. So let's begin with class example number 1. Sandy makes $2 profit on every cup of lemonade she sells and $1 on every cupcake that she sells. Sandy wants to sell at least 5 cups of lemonade and earn at least $25 per day. So the first thing we're looking to see and determine is, okay, what information in this problem is missing, or what is the 2 pieces of information that's unknown. And in this case, good. It's the number of cups of lemonade sold and the number of cupcakes sold. So it doesn't matter which is my x or y. For the sake of this problem, let's kind of be on the same page. We're going to say let x equal the number of cups of lemonade sold. And if x represents the number of cups of lemonade sold, I'm going to let y equal the number of cupcakes sold. Now that we've created our let statement, we're going to look at the clues in the problem that's going to lend ourselves to the system. Well, the first thing I notice in this problem is that it starts to talk about the profit that Sandy wants to make. Sandy makes a $2 profit on every cup of lemonade. Well, if each cup of lemonade is X, and she also will make $1 on every cupcake that she sells, where cupcakes are my Y, okay? And I'm just going to kind of erase that so it doesn't look funky. And she wants to earn at least $25 per day. So that whole phrase there lends itself to an inequality. If she makes $2 on every cup of lemonade, that represents 2x. Plus, if she makes $1 on every cupcake, I'm going to represent that as 1y, or just y. And we're going to say that amount must be at least $25. In other words, it can be 25, but it must be more than that. So we're going to use greater than or equal to. The next major constraint that I notice is that it says that Sally wants to sell at least 5 cups of lemonade. Well, once again, if x represents the number of lemonades, how can I write that as an inequality? Good. X would have to be greater than or equal to 5. And then the final the final range restriction here isn't really listed, but we know intuitively that, well, the number of cupcakes she sells has to be greater than or equal to 0. She, in theory, could sell no cupcakes, right? Maybe nobody wanted to buy cupcakes. But she also could sell more than that. We just know intuitively that she can't sell less than 0. So now that we have our inequality in our system, we now want to start graphing. Now, when we're graphing, we want to make sure that we're including the following components. You do need a title, you do need to label your axes, and you also need to clearly indicate what your intervals are. So let's start by labeling our axes because that's a little bit easier. We could take a look at our let statements, and that's going to tell us which is my x-axis and which is my y-axis. In this case, we're going to label our x-axis as the number of cups of lemonade sold. And then we're going to label our y-axis as the number of cupcakes. I look at the problem as a whole, and it really is talking about just what Sandy is selling here. So I'm going to call this graph Sandy's sales. And remember, your title can be a little different. It just has to pertain to the problem. Now, the next thing I want to do is to create intervals. And before I just jump right in, we already have some information that's really going to help us to create really accurate intervals that's going to make our graphing a little bit easier. So I notice here in this first equation, the 2x plus y is greater than or equal to 25. I'm actually going to write that as a linear equation. Now, if I were to graph this, some of us might say, let's put this in slope-intercept form, y equals mx plus b, plot the y-intercept, and then count up and over for the slope. However, I look here and I notice, well, this is already in standard form, and we know the benefits of standard form is to find the x and y-intercept. So that's what I'm going to do first. I'm going to look here, and if I say, well, if x is 0, and I cover this up, right, well, we can know that y would be 25. So now we have a y-intercept, and then we're going to reverse it. Well, if y is 0, I can cover this up, then that would say x would equal 12.5. So now we have an x and y-intercept that we know needs to exist in our intervals, and that can help us make a really good decision about what intervals we want to do. Now you have a choice of what intervals you want to do. I'm going to start off by looking at my x-axis, and I'm going to choose intervals of 2. I'm going to use nice tick marks to indicate where these are labeled. For my y-axis, I know that my y-intercept needs to at least reach 25. I'm going to do intervals of 5. Now we can start graphing. So I'm going to kind of match the color to each inequality. So to first graph 2x plus y is greater than or equal to 25, I'm going to look at my y-intercept and my x-intercept. The first thing I'm going to do is plot my y-intercept, which is 0, 25. I'm going to look at 12.5, 0 as my x-intercept. And I'm going to create a solid line because we see that it's greater than or equal to. So as you're doing this on your paper, I'm going to do it on my smartboard, making sure that you're using a ruler. And we understand that this boundary line should be solid. Now this specific inequality is representing all the different possible combinations that Sandy can utilize to earn at least $25 per day. So to graph this solution region, I now need to shade in everything above this. Every ordered pair represents the number of lemonades and the number of cupcakes that she can sell that would help her reach that minimum. Sorry, I didn't like the way that was shaded, so I have to reshade it. All right, we're not done. So now I'm going to switch over to green, and we're going to plot x is greater than or equal to 5. That domain restriction is really coming and stemming from that constraint that she wants to sell at least 5 cups of lemonade. Well, I know x is greater than or equal to 5. I go to 5 on my x-axis. I'm creating a vertical line. Since it's greater than or equal to, I kind of know here that we're dealing with a solid boundary line. I'm going to use a green color to now shade everything to the right of that. And then we can start to see our solution region really starting to appear here. This area that it's overlapping. Now the final line that we could in theory technically shade in is y is greater than or equal to 0, but we kind of know once we shade it, this region right here is going to be the region of overlap. So I'm going to make that really clear by kind of creating this grid. You can also just create an arrow and label this as your solution region. Now let's discuss really quickly what this solution region actually means. What this means is that any ordered pair that exists in this shaded region represents different combinations of cups of lemonades and number of cupcakes that Sandy can sell in order to meet all of those constraints she listed. So for example, I'm going to get rid of all of this. If I use the point 1410, which is going to be right over here, this is one possible combination that Sandy can do in order to reach her minimum of a $25 profit per day, where she's selling at least 5 cups of lemonade. However, we just need to create one possible solution. So we're going to list any point. Let's say we choose 10, 15. We're going to write that ordered pair here, but I will not accept just an answer of just an ordered pair. You do want to analyze what this means in the context of the problem. What this means is that Sandy can sell 10 cups of lemonade and 15 cupcakes. Now, if I asked one question further, I could say, well, how much will she earn? Then your job would be to take that coordinate 10, 15 and plug it in to this equation here to determine what is her total profit. Well, not even the equation, the 2x plus y to determine what would be her total profit. All right, and in theory, it should be over $25. All right, I hope example 1 kind of made sense. So let's move on to class example number 2. In 1 week, Ed can mow at most 9 times and rake at most 7 times. He charges $20 for mowing and $10 for raking. He needs to earn more than $125 this week. What are different possible combinations of jobs he can do? Once again, we're going to start this problem by identifying what is the information that's missing. We have 2 unknown values. Good, we have the number of times Ed mows and the number of times Ed's going to rake. So I'm going to start by creating my let statements. In this problem, I'm going to let x equal the number of times Ed's going to mow. And then we're going to let y equal the number of times Ed rakes. We're going to start by creating our system by looking at some important information in the problem. So if we start with green, we're going to see that in this part, I noticed that he says that he wants to mow at most 9 times and rake at most 7 times. So in this problem, he wants to mow at most 9 times. I'm going to underline that in green. And if he wants to mow, well, if x represents the number of times that Ed wants to mow, it needs to be anywhere between 0 times to 9 times. So that's our domain restriction right here. I'm going to write that as a compound inequality. 0 must be greater than or equal to, x must be greater than or equal to 0, and it must be less than or equal to 9. It has to be somewhere between 0 and 9. The next one that I'm going to see over here is that he said that he only wants to rake at most 7 times. Well, if y represents the number of times Ed wants to rake, what inequality would represent that scenario? Good, another compound inequality. Y must be greater than or equal to 0 and less than or equal to 7. Finally, I see some really important information about the profit, right? He charges $20 for mowing and $10 for raking. He wants to earn more than $125. Well, if he charges $20 for every time he mows, that's 20x, plus $10 for every time he rakes, that's 10y. It needs to be greater than 125. It has to be more than 125. So, taking a look now at the system, you're going to now pause the video and you're going to graph this. Please keep in mind kind of labeling your axes, creating a title, creating nice clear intervals, and then using a straight edge or a ruler in order to graph each boundary line accurately before shading. When you're done, you're going to want to identify one possible solution, which remember will vary, and there's many different answers there. And then when you're ready, unpause the video and we'll reveal the answer. All right, so at this point, hopefully you've identified all the answers for class example number 2. So let's take a look if your graph matches mine. You're going to notice that there is a dashed line for the 20x plus 10y is greater than 125. The solution region that you should have shaded, I'm going to shade here in this like green foam color, is over here. Every coordinate point that exists in that shaded region represents different possible combinations of jobs that Ed can do that will hit all of his constraints. Now your final answer will differ than mine, but I chose 8, 5. And I said, well, this one possible solution means that Ed can mow 8 lawns and rake 5 times. I also went ahead and calculated that total cost. You didn't need to, but if we were to say, well, how much is he earning from that possible combination? In this case, he would be earning $210. And we notice that every ordered pair that exists in this shaded region is a perfect combination that hits all of those constraints that he wants. So hopefully that made sense for class example number 2. On the back side of your notes, you're going to see this tried out example. This one's a little tricky. I would like you guys to try your best to go through, read the problem, and write a system of inequalities that matches the scenario. Please keep in mind that they do give you the let statement, and we are not using x and y, but we instead are using c and w. Once you've read through it, you're going to write the system, and you're going to answer some of the questions that are listed there. When you're ready, unpause the video, and we'll reveal the answers. All right, so at this point, hopefully you finished the tried out example. Let's start by going over it. You're going to notice I didn't write a let statement because it was in the problem, but I did come up with 4 different inequalities. The first inequality is really representing the number of hours that he wants to work. In this case, Jody only wants to work at most 50 hours. So the number of hours he's working as a carpenter and the number of hours he's working as a web designer needs to be less than or equal to 50. I then noticed that he talked a lot about his profits here, how much he wants to make. Well, he charges $34 as a carpenter and $75 an hour as a web designer, and he wants to make at least $2,350. That's this inequality here. We then looked at different constraints that he also said, right? He doesn't want to work all the time. So he wants to work at least 10 hours per week as a carpenter. All right. And then he also didn't say anything about a web designer. So we said W must be greater than or equal to 0. In part B, it said, what is the maximum amount of money that Jody can make in a week given the system in A? Well, this required us to really think about what information can we plug in. Well, if I know that the maximum number, he wants to work at least 10 hours, we're going to plug in 10 for C, and we see that W needs to be less than or equal to 40. Now we have an ordered pair that we can plug in to see exactly how much he's earning. We can take this expression 35C plus 75W, plug in 10 hours as a carpenter, 40 hours as a web designer, and we're going to get the final answer of $3,350. In part C, all they're asking is to actually label each of the lines. I used 3 different colors to indicate the different constraints. And then in part D, they asked us to really switch gears a little bit. They said find the coordinates of point A, which is this one here, by actually solving the system. So we looked at the line in pink and the line that I showed in blue, and we solved the system of equations to determine the point of intersection. And we noticed that the point of intersection was 3515. Sorry, I just mixed up my X and Y. All right, from there, what does the value of C that you found in the solution represent about the number of hours Jody can work as a carpenter? Well, that really just represents Jody can work a maximum of 35 hours in order to make more than $2,350 while still working less than 50 hours. So that point really talks about hitting all of those constraints. All right, now that you've actually tried out a problem on your own, you're now going to move on to the station activity. When you're ready, you're going to move on to Google Classroom. You're going to access the station activity. Hopefully you can get a hard copy. Please making sure that when you get to the backside, they're really going to start asking you to graph. These are some things that I expect to see. After creating your system, you're going to label your axes. You need to create clear, distinct intervals. When graphing your boundary lines, you're going to want to make sure you use rulers and different colors if possible. And then finally, writing your possible solutions not only as ordered pairs, but also as a complete sentence in the context of the problem. We've done a lot today, so let's reflect on some of the work we did. When looking at some word problems that lend themselves to a system of inequalities, the first thing we want to do is identify what are the missing or unknown values. That lends itself to writing a let statement. After we've written the let statements, we're going to create a system. It's really important that you're taking all of that information in the problem and creating a clear system that hits all of the constraints. Then you're going to set up a graph by labeling your axes and creating clear intervals. You're going to graph your system by using a ruler or a straight edge and then clearly indicating if our boundary lines are solid or dashed and then shading in the correct direction. Sometimes you might need to use a test point. Finally, looking at your overlapping shaded region, you're going to identify one possible solution, but making sure that you're interpreting, not just telling me the point, but telling me what does that point mean in the context of the problem. So we've done a lot today, and it was a really meaty lesson on how we apply systems of inequalities. I hope this lesson helped. You can move on to some other resources. Thank you so much for watching, and I hope you enjoyed this video. Thanks, everyone. Bye.